Hello and welcome to the lecture Encoder-Only Transformer Model. In this lecture, we discuss Encoder-Only Transformer Model, and as a part of it, we start with BART architecture. Then we try to understand the masked language model and next sentence prediction mechanism. Then we discuss the BART architecture and pre-training and fine-tuning methods of the BART, and then we discuss few successors of the BART architecture. We conclude this lecture by discussing the application of the BART. An encoder transformer model is basically use the transformer encoder for its purpose. So, an encoder-only transformer model is a neural network architecture that uses only the encoder component of the transformer to process and understand the input. Now, here in this figure, you can see that this is the main architecture, this is the encoder part, this is the decoder part. And is this encoder only model, which essentially is basically a multiple stack of encoder layers, is basically this encoder, one encoder part use this part of this transformer. So, which a encoder is basically consists of a single encoder block. It basically stops self-attention mechanism and feed-forward neural networks. As you can see here, this multi-rate attention is a self-attention and this is the feed-forward. It essentially captures the relationship between all words in a sequence simultaneously. So, as a whole, the encoder-only models is a series of encoders which every layer of the encoder or every encoder here is essentially the encoder part of the main transformer architecture. Now, this encoder only model is basically bidirectional in nature. What does this mean? This model considers both left and right context. This property makes these models highly effective for tasks that require deep language understanding. So, if you see that there is a sentence is given, we are trying to understand a word, this word, how it relates not only to its prior word with relation with these future words. So, this particular encoder only model that we'll see in next few slides is very much efficient to understand the language or the sentence meaning or analyzing a particular sentence. So, the popular models in this encoder-only transformer model is the BART that are trained to produce rich contextual embeddings which are then used for application like text classification, sentiment analysis, named entity recognition, question answering, etc. So, unlike decoder based model, this encoder only transformer focuses on analyzing and representing input rather than the generating text. So, in our next, we'll basically try to understand what do we mean by BART. Now, we start BART. The BART stands for bidirectional encoder representation from transformer. This is basically a powerful language model that we see in subsequent slide. The main thing of BART is it's an encoder only model and it's a bidirectional. It is introduced or proposed by Google researcher at 2018. In literature, what we have observed that it significantly improved many NLP tasks by learning the bidirectional representation of text using the transformer encoder. So with this very naive or very brief background, we try to understand what is the basic architecture or basic training procedures of BERT. But before that, what are the major problem of the existing language model prior to BERT? The language models basically used a unidirectional approach. That means they use either left context or right context. But language as its nature is bidirectional, or language understanding is bidirectional. But why this language model unidirectional? That directionality is needed to generate a well-formed probability distribution. So that is not by these unidirectional models. And words can see themselves in a bidirectional order. So what we have understand that prior BERT most of the language models are unidirectional. So are they missing this either left context or right context? Now, if we find out what are the basic things of unidirectional, bidirectional, the architectural way. Now you can see here. Now this sentence you need to understand. Go to the bank of the river. Now if we consider the left context, that this is basically the start of this, and this is only use the kind of left to right model. So go to the bank. Now using this particular part of the sentence, can we figure out what the bank means? It may be a financial institute, it may be a river bank. But when we come here, bank of river, then we only understand that this is the bank. This is the bank is related to river bank. So that is the one of the problem of unidirectional context. But if there is a bidirectional context, that the context flow not only from left to right, it is right to left also, then this thing also will come up when we try to find out the meaning of bank. Not only these prior words will come in, the future words also come. Then it more easily we understand what is the meaning of bank. That is the major advantage of bidirectional context analysis. And basically BERT is going to utilize this advantage, and thus it become a very popular and efficient model for language understanding. Now, how this BERT is different from common language model? As we said, unlike common language model, BERT doesn't handle special tasks with prompts. It basically don't use prompts, but rather it can use to special tasks to fine tuning. So it is basically first pre-trained with a large or a huge text corpus and then fine tuned to a specific task. What we said earlier, BERT has been trained with the left as well as right context, hence bidirectional, unlike the common language model. Definitely prior to that. So BERT is not specifically designed for text generation because it don't have a decoder part or decoder component or a next token prediction task. This is also generative in nature. Since BERT is basically encoder based, so it more efficient by virtue of its bidirectional context analyzing. It's very useful for analyzing the sentence. Another important property that BART is going to use the masked language model and useful for next sentence prediction task. Both the case, this is very useful. So by this way, BART is different from these common language models. Now, BART is a masked language model. So first we have to understand what we mean by masked language model. A masked language model is a training method used in some language models where certain words in a sentence are hidden or masked, and the model learns to predict the missing words using the surrounding context, and in this way it is being trained. For take an example, this is the original sentence. Ron went to football ground to play football. Now for training purpose, if this ground word is masked and this football word is masked, and what is basically this model is going to learn that learning the context and can they predict this masked word, and prediction should be ground and footballers. So in this way this is done. So during training, some tokens in a sentence are replaced with a special mask token. The model then tries to predict the original word, and by doing so it is being trained. So the model learns by minimizing the difference between predicted word and actual word. So in this way this model is being trained. Now mask out the k% of input words and then predict the masked words. In general, k is 15%. So this is Ron went to football ground, that is mask, to play football. Now if we use the too little masking, the value is k is very less. It's too expensive to train. But if you use a too much masking, that not enough context to learn. The learning is big. So this is the general understanding of masked language model. Now the masked language model is this small issue that mask token never seen at find. So what generally is being done to countermeasure this thing? That 15% of the word to predict, but don't replace mask with 100%. 15% token is masked, fine, but out of them all the tokens are not masked. So 80% time replace with mask, when to field, when to mask. 10% of time replace with random word, when to field, when to school, and 10% of time keep the same, when to field, when to field. So it basically solves this particular problem. Okay. The next thing is next sentence prediction. Another thing that another way it is trained to learn the relationship between sentences, predict whether sentence 2 is actual sentence that precedes the sentence 1 or a random sentence. So if we say write sentence 1, Ron went to cricket ground, he scored 55 runs. Definitely this sentence can follow this particular sentence 1. But if we say Ron went to cricket ground, the sun rises in the east, is not the next sentence. So in this way that the next sentence prediction can be learned. Now when we see the architecture of the BART, you can see that it basically uses the the encoder part of this transformer model. So inputs, then there is the input encoding, and then the positional encoding is basically added to the input encoding, and then it comes to the actual encoder part, which basically consists of multi-rate attenuation and add normalization. Then again feed forward, and again there is some residual connection here. And this is the n time. So n may be 6, n may be any number. Then the input, whatever is processed by this encoder, is coming to the linear layer, and then it's a softmax to the output properties. So this is going to the next encoder layer. So in BART there is a two different type of architecture. One is BART base, that is 12 encoder layers. So this layers is 12 times, basically layer by layer. A series of 12 encoders layer is stacked. The size of the hidden size of the feed forward layer is 3072 and 12 attention head used. And BART large 24 encoders layers. This feed forward layers is 4096 and 60. So these are basically two category or two different BART architecture that have been proposed. Now, how it is different than normal vanilla transformer? The embedding vector is 768 and 1024. 768 for the BART base, 1024 for the BART large, two models. Positional encoding are absolute and learned during the training and limited to 5 positions. The linear layer heads changes to according to the applications. So, like the way BART is basically used word-based tokenizer, which also allows sub-word tokens, vocabulary taken 30,000 tokens. So these are the some meta information that used by the BART architecture. Now, we have to understand how the BART is basically work. So there is a two major thing. One is speed training and one is fine tuning. So this, how if we say a pre-trained BART, that how it basically fine-tuned with this question answering. So now that we have to understand this. But first we have to understand BART use the both left and right context to understand the sequence. Let's take a hypothetical sentence for this. Now if I say I sit in a river bank to see the sunrise. So in this sentence the river, this river, which is left context of the to see the left context and to see the sunrise, the right context of the word bank. Now this bank word, river is the left context and to see the sunrise right context. And you can see, if you understand, this bank is a river bank, not a financial institute. The two contexts are important to understand. So both the contexts are helping to understand that what bank is a river bank and not the financial institute. And exactly these things is being learned by the word, since it is a bidirectional. Okay, so in a particular that question answering, BART is fine-tuned to this specific task. Now, what is the input representation of this BART? There is a three major input representation. One is token embeddings, one is segment embeddings, and one is position. Now, here take this from this main paper, that this is a CLS token, that's starting off in sentence, that my dog is cute, then separated. This is another special token. He likes play or playing. This is again separated. Now token embeddings is basically kind that it will go into a token first, that E of CLS. So E of So these are the different tokens. Then you can see that segmenting between which segment it is. So this CLS to this separator is one segment A, already, and he to separator is segment B. So these two different segments. So you can say different sentence in that way. And positional encoding, that it is at which position these tokens are. E0, E1, E2, E3, E4, E5, E6. So this is the positions, the relation of these tokens. So this is the input representation of the word. Okay. Now here in this input representation, the key concept how this model processes the text for understanding it. So BART doesn't take the raw text directly. As we discussed, it converts it into the structured numerical inputs, three main components: token embeddings, segment embeddings or sentence embeddings, and position. Now what do we mean by token embeddings? As we said, BART first splits text into tokens using BART piece token. Example: playing, play. Each token is then converted to a token ID and mapped to a dense vector that is embedding. And by this we can get this, that E of CLS, E of I, and so on. Then comes the segment embedding. These tell BART that which sentence each token belongs to. So this CLS to separator, this one sentence 1, and he to this again separator sentence 2. This is used specially for sentence pair type. Task is equation answering. So two types: sentence A assigned 0, he is cute, and sentence B assigned 1, he likes playing. CLS, my dog is cute, is separator, he likes playing separator. Where BART used two special tokens named CLS is added at the beginning of the sentence. Is for classification task. And separator, separate sentence are marked into the input. So this is the input representation of the BART. Okay. So next comes the position. So this position embedding, BART doesn't inherently understand what order or position embeddings are added to indicate the position of each token in the sequence. So position 0 is first token, position 1 is the second token, and so on. So this is the position embedding. The two major parts of the training of the BART is one pre-training and one is fine-tuning. So we start with pre-training, that to generate each training input sequence, two spans of text are sampled from the corpus, which are refers to a sentence, even though they are typically much longer than the same sentence. And then we sort of. So first sentence A embedding, the receive first sentence is the A embeddings, and second is the B embedding. Now 50% of the time B is the actual next sentence that follows A, and 50% of the time it is a random sentence which is done for the next section prediction task. So in this way the sentence are splitted from the corpus and this being given to the BART for the training. They are sampled such that the combined length is less than 500 tokens. That is the total input number of input tokens. So this LM masking is applied after the BART piece tokenization with uniform masking rate of 50% and no special consideration given to the BART piece. So this is the pre-training part. Now you can see the pre-training is this. This is the token 1 to token n, this separated token 1 to token n. So this is the two sentence. This basically first sentence is its A embedding and second is B embedding. So these two sentences. Mass. So this is the mass sentence A, mass sentence B. and then it will give the corresponding these tokens. Okay, so this is the embedding of the tokens, and then this particular that this at the output of this, so that in this way BART is being learned or trained. Okay, fine. So next come the fine tune. Fine tuning means start with a pre-trained BART. Once BART is trained the way we have described, it is pre-trained, already understand the language broadly. So we will add a task specific layer. Okay, so to train the whole model or most of it on data set. That means this. Fine tuning means this. Basically, using a pre-trained model, we are basically using a small set of data to train for the special or spatial task. The task specific model is formed by incorporating BART with one additional output layer. So the minimal number of parameters need to be learned from the scratch. So all these pre-trained models parameters are fixed. Only one layer is added, and that among the tasks, two are sequence level task and token level task. Okay. In the figure, this E is represent the input embedding. So these are the input embeddings, and T is basically the context, the contextual representation of the. Here is the special symbol classification output, and separated is the special symbol to separate non-consecutive token sequence. So this is the way, and these are the different tasks. So different. So this is the question answer pair, the question paragraph, and in this way it is being trained. It's fine tuned. So for fine tuning, most model hyperparameters are the same as in pre-training, with the exception of the batch size, learning rate, and the number of training blocks. So the most of the model hyperparameters are the same for this fine tuning. Only for pre-training with some exception, batch size, learning rate, and training box. Dropout probability is 0.1, and the optimal hyperparameter values are task specific. So in this way, for the different purpose, the BART's models are being fine-tuned. There are few methods which has been proposed after the BART. One is ROBARTE. ROBARTE is robustly optimized BART approach, which is developed by Meta. It's basically an input version of BART that improves the performance by defining the training process rather than changing its architecture. It basically removes the next sentence prediction task and trains on much larger dataset for longer periods. And this uses dynamic masking, so the model sees the varied example during learning. So this is basically use some new concept of dynamic masking and trains a much larger dataset. This optimization allows ROBARTE to achieve a stronger result as a wide range of natural language tasks. The next is ALBERT. This is basically a light BART, so it's some lightweight than the BART architecture. This is developed by Google Research and is a streamlined version of BART designed to reduce the model size and improve the efficiency while maintaining the strong performance. So what is done? The parameter sharing is used across layers, and factorizing embedding matrix that is used significantly lowers memory usage and speeds of the training. So computational cost is also reduced. And this ALBERT is also replaced the next sentence prediction with a more effective sentence order prediction objective. This leads a better result on various NLP lessons. Now, next is coming the digital BART. The digital BART is developed by Hugging Face. This is a smaller, faster version of the BART that created using knowledge distillation, which compared the student model learns from the larger pre-trained model. So it retains most BART's language understanding capabilities while being about 40% smaller and significantly faster. That makes it well suited for real-time and resource content application, which only the modest of language. So digital BART is basically a knowledge distillation being used here to that where compact student model learns a larger pre-trained model. So it basically retains most of the BART's language understanding, and it is a 40% smaller, significantly faster than that. So it is good for real-time and resource constrained applications, but without compromising the accuracy. So finally, what are the application of BARTs? It's very much used for question answering like chatbot, sentiment analysis, text classification, named entity analysis, search engines, Google search BART to better understand the queries. So in this lecture, we introduced first the encoder-only transform model. We specifically concentrated on BART model. Then we understand what is asked language model and what do we mean by next sentence prediction. Then we discuss the BART architecture, then pre-training and fine-tuning. Then we discuss a few successors of the BART and we conclude by discussing some application parts. Now in next lecture we discuss decoder. Thank you.